Okay, thank you, Ankush. Let's see, last night, actually talking about programming, I hacked up an autograder for the first assignment. I'm hoping it'll be additional incentive for you to do the homework. I think it's important not just to sit here and just listen to what's going on. Ultimately, it's all about programming, right? So if I give the opportunity for you to program, I would really encourage you to take advantage of it, and the autograder is a way to check your work, to an extent. What it doesn't check, because to check that would be really difficult, is whether you are actually writing appropriately linear programs, or if you unnecessarily copy things, for example, right? That's part of the spec in a sense, but how would I actually test that, right? You don't have to call the copy function. You can write your own auxiliary function called myOwnCopy, okay, and call that. So the only way to really test it would be for me to run a space profile on the code that you write. And if you copy too much, you use too much space, okay? I'm not going to go that far, okay? So I'm not going to do that. So that's your own responsibility. Okay, so I will add to that as we go along. I'm not sure where we're going today because in part I'm reacting to what happened in the first lecture on the questions. So, but I'll put out some new assignments as we go along. And some of them will be programming assignments. Okay, so originally I said, and this is still true because it's true of all my work, that my lectures are about the connections between logic and programming languages. So yesterday, we just did programming languages. We really didn't do logic. Or if we did logic, I hid that from you, okay? So you were actually, might not have noticed, but we were actually doing logic. And today, I'm going to try to expose that, okay? The fact that we really are doing logic. And so I want to go back and forth between programming languages and logic. And depending on how the lecture goes, I might do that 2 times, okay? Because in each case, there is something to be learned from the logical side that we can then translate into the programming language side and learn something from that, okay? It's one of these things that whenever you find a good explanation for something, then you say at the end, well, I could have done that directly. I didn't really need the logic. And that's, of course, true. But in the discovery process, it's very important to be aware of these things, about these connections between programming languages and logic, because yeah, when you're all done, yeah, it kind of looks, everything looks like inevitable. But while you're working on something, a new programming language design, things are not inevitable. You might make mistakes. You might make things that are not right exactly the way they should be, or you don't actually know how to proceed. And what I'm going to show today are examples of that happening, okay? Because it happened in my own work in different ways. It happens to me like all the time, okay? So let's start with that. Let's look at this type system, okay? So ignore the second board there. I just wanted to save some time. Okay, so these are the rules from yesterday, just summarized, okay? So you introduce something of type 1, which is this value. You match against something of type 1. And then you have a match here. You can introduce a pair, and you can match against the structure of a pair. You can introduce an element of a sum by injecting it into the sum with the appropriate label. And you can do cases over what element you're in. And for each branch, you have a way to proceed, okay? So that's kind of the whole type system. And for variables, well, we just look them up in the context, and we have to be careful with the discipline because, for example, here we have gamma and delta. We have to split it up because we're doing linear programming, okay? We have to use every assumption, every variable exactly once when the program runs because we want garbage-free thing. At the end, everything should have been used. Okay, so one question yesterday was, do we have a dynamics, a specification of reduction for this language? And ideally, I like to have something where it gives you an intuition, or it shows or demonstrates that there will be no garbage, okay? So we somehow want to know that our intuition about not creating garbage is actually correct, right? If that's not correct, then we made a mistake somewhere, right? So this happens a lot. The reason you prove certain theorems is not because they're difficult, but because they check your work. Now, I'm not going to prove any theorems in lecture. You get that enough in other lectures. But I'm going to set it up in such a way that you can prove them yourself if you want to, because I'm giving you the intuition. Most of the effort in proving is actually constructing the correct deductive system and not doing the real proof. The proof is usually just routine, right? But setting up the system correctly is the hard part, so that's what I really want to teach you. Okay. Okay. So, so one thing which is good is when you try to devise the dynamics, how to run the program, you want to show things like type soundness, which Amal talked about yesterday. We want to prove something slightly different here than type soundness, because we really care about an additional property, which is there's no garbage. Okay, so it's really a different property they want to prove today. Now, when you prove properties of a dynamics, one thing you can try to do is to set up a close correspondence between the static rules of inference and the dynamic rules for running the program. The closer the correspondence is, okay, the easier the proof is going to be. If there's a big difference, okay, you're going to have a big difference, big gap, and your proof might get very complicated. You might not know how to do it. But if they're very close, then you would be able to do that proof, like simply and routinely in many cases. So we're going to try to set it up so that the rules are very close. So at runtime, okay, if you have a judgment such as gamma E colon A, okay, so the expression E, when you run the thing, is actually a thing you execute, thing you evaluate, okay? A is going to be a type for that, and probably at runtime you won't actually care about that. You don't want to carry it around, okay, because that might be expensive. And you shouldn't have to. But what does gamma correspond to? So here we have a typing for the variables. So what should that correspond to at runtime? Yeah? Should be a variable map from variables to values, okay? And so we need this map. Okay, let's call that eta. And we wanted to match the context gamma, and we have to define what that is. And we communicate many of our ideas just by using inference rules, so we can do that by inference rules. So what are these variable maps? Well, the empty variable map matches the empty context, right? If there's no free variables, then there are no bindings, because we don't refer to anything, okay? And so what if we have a gamma with x colon A? Okay, what environment matches that? Okay, so x is mapped to some value v, right? So we should have that, because the prescription is when your program runs, x should be bound to something, because when you evaluate e, you should have binding for all the variables in it. So we need x gets mapped to v, okay? But what about gamma? Yeah, so we have a further environment, eta. When is this well typed? When does it match our assumptions? So what do we need to say about V?
It's of type A.
V is of type A. And what about eta? It has to match gamma, right? And what about our runtime values? Okay. So the way we describe the values, they're always closed. They don't have in themselves any free variables. So when you say, I want to evaluate this program of type nat, you want to get something like successor of successor of successor of 0, not something like successor of successor of y. That's not a valid answer, right? So the values that we compute, they should always make sense in the empty context, right? By the way, I'm using terminology here. I call this an environment, and I call this a context. Okay. There are other terminologies. That's what I usually say. Okay, so this is how we can show that an environment matches. Okay. So then what we want to do is we have an environment eta, we have an expression E, you want to evaluate that to some value V, okay? And in order to do this, we want to assume that if E is typed in context gamma of type A, and eta matches gamma, then what should the type of the value be? Should also be of type A, right? When we start with something of type A, we want the answer to be also of type A, but we also want it to be the answer. So this should be a consequence of whatever we do, okay? So these two things are a precondition. Under those conditions, we should be able to run this program. Are we good on that? Okay. So this is all well and good, but there's a problem here, which is this rule, okay? Why is that a problem? Okay. So let's just think about that particular rule. So we have an environment eta, and we evaluate in the pair E1, E2. Okay. So pay attention sometimes the order in which I write things, because when you write things on your own, in your research or whatever, you should also follow a certain structure, right? You always write the things that you know, which is not necessarily the way you usually often read a rule of inference, okay? You might say, if E1 has type A and E2 has type B, then the pair is that. Well, that's not really what we want to say. We want to say, for the pair to have this type, E1 has to have type A, E2 has type B, and we have to split the context. So you write in a different order than it looks finally on the page. There's a dynamics to that, okay? So that's what I want to do. Now, I know I'm supposed to evaluate E1, some value V1, and I'm supposed to evaluate E2 to some value V2. And we already know what the answer is going to be. What is it? The pair V1, V2, right? But what are we going to put here for the environment? We have to split the environment, right? Put part of it here, part of it there. But how do we split the environment when you run your piece of code? You didn't care about having these, having a source representation of these where you can look at an expression, you see which variables are free. You would take eta restricted to free variables in E1, put that here. You take eta restricted to the free variables V2 and put that here. Okay. That's not really a feasible thing to do. Okay. Yeah? You have a question? Okay. All right. So we have a problem here, right? We're trying to describe how the program runs. Now, if you think about it intuitively, how would you run the program? Yeah?
Why isn't it feasible to do the split as you said?
Okay, well, first of all, if the split, then every time we have a pair, we have to traverse the expression and to see what the free variables. Or in our representation, we have to store the free variables with these expressions. That's not really what you want to do. And also, furthermore, eventually you want to compile this into some lower level language, in my case, eventually C. And then how you're going to split the environment. It would be a very difficult thing to implement. You don't really want to do that. So what do we do instead? Yeah? Right. Once it passes a type checker, we know that everything should be used exactly once. So we could just be able to pass the whole environment eta to here, and the whole environment eta to here, right? And this will use some part of it. This will use up some other part of it. In the end, nothing should be left. Okay? But how do we now express that? That's the complicated thing. Okay? So one way to do this, and I called this yesterday the subtractive approach. Okay? Maybe I'll try to use colored chalk. Okay. Red is negative, so that's the subtractive approach. Okay. In the subtractive approach, we pass eta into here. We run this program, it uses up some part of our environment, and returns to us a thing that it hasn't used yet. Right? You subtract from the environment the thing that you use. You deallocate them as you read them. So you would get back some kind of eta 1. Okay. Then you pass an eta 1 into here. Okay. And then what you would get out at the end? It should be empty. And then here would be empty, except if you have a nested pair, E1, comma, E2, comma, E3, you can't do it quite that way, right? So what would you do in that case?
Generalize the output.
We have to generalize the output. So you pass an eta here, it gives you back an eta 1. You pass in an eta 1, you get back an eta 2, and then you output eta 2. Right? And at the top level, when you start your original program, you give it an original environment. When you evaluate the final value v, there should be nothing left at the end, because you have consumed everything. Okay. So this is called the subtractive approach. And it also corresponds to a type checker. Okay. How does it correspond to a type checker? So we have a gamma down here, and we pass the gamma into here. When we type check E1, this will use some of the variables in here, but will not use all of them. So we output in the type checker some kind of, I don't know, some delta. Okay. These are the things that were not referenced by E1. So there will be a subset of gamma, right? Some things will be referenced because it's a linear thing. Some things will not. We put those here. Yeah, you have a question?
Yeah, is there a more direct way to represent all of the subtractive stuff that's happening here in our logical rules? Because it seems like a lot could get hidden under the hood, so to speak.
So the question is if you can represent directly in the logical rules, you mean the rules over there?
No, on the left side, where we've kind of scribbled on our logical statement in red what
Yeah.
we're doing with these subtractive rules. And
Okay.
yeah.
Yeah, so I'm taking some shortcuts here. So the thing with the etas is clear, right? So let's do the logical rules. So in the subtractive approach, I have a context gamma that I start with, and I want to check a pair E1, E2, okay? And I know I want to be of this type. So what I do is I take gamma, and I pass that into E1. Okay, so this might have more things than are actually allowed to appear in E1. And I get out some things that are not used. Okay, then I come into here and I pass delta into here. I check E2. That will use some things. Oh, of type A. E2 will be of type B. And there's some other things that it doesn't use. Delta prime. Okay. And then overall, the things that are not used are the things in delta prime. Okay. And so whether this works or not, okay, you don't know this from one rule. You'd have to look at all the rules and you have to change them all. And you have to change your basic judgment from saying in gamma something has type A, from with the input gamma, given an expression, it has a type and it has some output context, the things it didn't use. Okay? Is that okay? So could you write the rest of the rules now? You probably could, right? I mean, just take one. Let's say the variable rule. So how do we change the variable rule? Okay, so we have an input. One of them must be X, otherwise X wouldn't have type A. But there are some other things, gamma, that are unused, and we'll just pass them out. Right? Does it make sense? And the sum rules are a little more complicated, but I don't want to do that because actually I want to implement a slightly different version. So this is the subtractive one. I want to call you the additive one. So it turns out that the subtractive one has a problem. Well, it has several problems. One issue is that when you execute your program, it forces you to go left to right. You have to evaluate E1 first to even know how to evaluate E2. Okay. But really, in a pair, you should be able to run the things in parallel, okay? But you can't if you use the subtractive approach. So let's try the additive approach, okay? Okay, I'll go back to just white. So in the additive approach, looks like this. You have a context gamma, okay? You have an expression E is type A, and we output some kind of output omega, okay? And these are the variables actually used. So these are not the remainders, not the thing that we haven't used, but the thing that we actually did use, okay? Now, it's not obvious immediately that this should make sense, right? This is just a hypothetical. So let's look at the rules for pairs, because that was one of the critical ones, okay? So if we have gamma, and we want to check that the pair E1, E2, oops, E1, comma, E2 has type A cross B, how would we type check this? Yeah?
We type check E1 and 2 with the same gamma.
We type check E1 and E2 with the same gamma. Hopefully they'll have type A and B. Yeah?
We get omega 1 and omega 2 respectively.
So we get an omega 1 and we get an omega 2.
And then we merge them to return from our double expression. And if they have the same variable, then we get an error.
Yeah. So then we merge them with this comma. Remember, this was a disjoint union. So we'll think this as being undefined if there's any overlap between the two. Okay? So undefined if they share a variable. Okay? And now the rule for evaluation, okay, would be something like this. We have an eta, and we evaluate E, pair E1, E2. Well, we already know, because the gamma is put into both places, eta should go here, and eta should go here as well. So we're passing the whole environment to both places. We get a value of V1, and we get a value of V2. Okay, so what else do we need here? We need to somehow, for this judgment, return the things that were actually used, that were consumed when you run this program. Okay, so something like small omega 1. Okay, so that's a sub-environment of this. It has some of the bindings, namely the bindings that were actually read. So it's a little bit unintuitive, because the ones that you read, you actually deallocate. But we're returning them because we want to match it without typing judgment. Okay? And then here we return some kind of environment omega 2. And then what do you return here? Yeah, disjoint union. Okay, we just put them together into one environment. And if our thing typed it originally, these should have disjoint domains. There shouldn't be any problem that the same variable appears in more than one place. Make sense? Okay. Now, eventually we'll get to a system that's not entirely linear. And so it is possible in that system that some variables actually are used in both sides. Okay. In that thing, for those variables, we allow an overlap here. Because that's okay, because the variable is allowed to occur on both sides. Okay. So this formulation is very nice because it extends eventually to what we want to do. Okay. Both for type checking and for running the program. Okay. All right, so now we need to revisit our theorem about this. Yeah?
So let's say we run a program that didn't get type checked. What goes wrong when we reduce the program using this rule? Where does it get stuck?
Okay. So first of all, not every program that doesn't type check will get stuck. Okay. So even if the thing doesn't type check, we can still sometimes run it. Okay. And in fact, during Amal's lecture, there was a question about that. So they are incorrect, ill-typed programs that still correctly execute. But if they get stuck, it could be because these output contexts here don't actually work, and they would actually like overlap if a variable is used more than once. Okay. But it's a good question because we also need to change our theorem about the system. Okay. So if we type check E and gamma of type A, that's really no longer the case. What is, we get some kind of output context. Yep. Yeah. Okay. So this is, now this, is it still the case that our environment is going to match our input context? In this approach. Yeah?
I don't really understand how we determine gamma and eta, I mean on the practical side. Why we cannot just use omega to calculate what variables are used by the subterms and then sum them up if they are disjoint or throw an error? Why do we still need eta or n gamma in this context?
Yeah, so we could do that in principle. We could calculate what are the free variables, and we could do the appropriate thing. And similarly here, we could calculate the free variables in E1 and E2. But this works on this level on the blackboard. But when you actually want to implement the language, it really doesn't work anymore. You can't really efficiently calculate the free variables and split up your environment into disjoint ones, and this uses this one, this uses that one, and so on. So there's nothing wrong in principle what you're saying. Yeah. But also, this gives us a way to actually describe, even though our motivation started operationally, it gives us a way to think about how to implement a type checker for this language. Okay. So one implementation would be, whenever you come to this rule, you calculate the free variables here, calculate the free variables here, and make sure to do the right thing. But when we get to more complicated type system, that really breaks down. Okay.
So if I understand correctly, we can actually easily compute eta and gamma when implementing the type checker, and not really compute easily omega and omega 2. Is it what you said?
When we write the type checker, we will compute omega. So we will get an input is gamma, the input is E. Maybe we have A, let's talk about that later, and we compute omega, the output.
Okay, so gamma is an input, not something we have to compute.
Right, yeah. So we're given a type environment. So if you have a top level definition, if you think about your implementation, you have to say plus of x colon nat, y colon nat gives you a nat. The reason you have to say that is that when we start, we have x colon nat and y colon nat here, and we have nat here. So we have that information while we're type checking E. We have to compute omega, yeah?
Is omega always like exact, or can it like be an over approximation of the actual variables used? If we have like non-determinism or like from type choice.
Right, so for the type checker, you want to make it be exact, because linear logic or linear type system is extremely exact. Every variable has to be used exactly once. So when we come to the theorem, we want omega to be exactly the things that were used in E, precisely those. How do we express that? So we have gamma E checks of type A, uses omega, eta matches gamma, the environment eta. Actually, let's think about the type checker first before, let's get rid of the, before we run the program. Can we relate back this judgment back to our original one? So if gamma turnstile E colon A backslash omega, then what would be true in our original type system over there? Any thoughts? Yeah?
Then I guess in context omega, E types to A.
Excellent. So in context omega, E is type A. Does that make sense to everyone? If we track exactly the things that are used in E, okay, then we should get that. We should also have that omega is a subset of gamma, right? Because we only want to pick out some of these assumptions. We don't want to make up new things. Right. Does that theorem make sense? Okay, so that would be a soundness theorem for this system. For this thing to be sound, it means that the output context is precisely the thing. What would be a completeness theorem for this? Yeah, you have an idea? If yeah. Okay. What do we do about this omega or gamma superset omega, omega subset of gamma? We're part of the assumption, right? And so this and gamma is a superset of omega. Then in gamma E, type A should produce that omega, right? If you put in something else here that's not related to omega, it won't make sense. But if you can put in a lot of junk here, it doesn't matter, right? Because only the things in omega really matter. Okay. So these things are actually, you can change the rules, and these things are then easy to prove, okay? Because we carefully designed the system. But of course, you never know that until you try it, right? I happen to know it, okay? Yeah?
If we were to sit down and try to prove this, would we need like two separate versions of our typing rules? Like being very pedantic, like
Yep.
the actual relation that's defined. One is a 3-piece relation, one is a 4-piece that has this extra omega.
Exactly. You would need two different versions of the typing rules. One defines this judgment. The other one defines this judgment. And you would have a proof that's saying for every derivation of this one, there exists a derivation of this one. And for every derivation of this one, under this assumption, you get a derivation of that one. And this would be inductive proofs. It would be something called rule induction because you examine each rule here, and then you construct a derivation over there. You examine each rule here, and with this assumption, you extract a derivation over here. Okay. Yep.
It seems to me that this completeness theorem allows omega to be an over-approximation to the variables that E uses.
No, because this judgment here is precise.
Oh, so the one on the left means E only uses the, okay.
Yeah, that's our original judgment, which is always precise. So no over-approximation in this one here, only in this one. Okay? Yeah?
Can you see the precise judgment as just the imprecise one, but then the output is the same?
Can you say this one here, if omega, then you get omega? Yeah, no, you cannot prove that inductively because when you come to the case of a pair, these things will be different. So you cannot apply your induction hypothesis in that case because even if at the top level these are going to be the same, here it's going to be some part of gamma, and here it's going to be some other part of gamma, and they're going to be actually disjoint. So if you try to prove it in the case where these two are the same, your induction will fail right at that point when you come to this rule. Okay? These are excellent questions. Okay. So then we just have to worry about specifying the dynamics rules for this judgment, right? But before we do that, maybe we should try to write out, okay, what are the properties we want for the dynamics to hold now, okay? So, so these are the properties of the type checker by itself. But what do we want the program to actually satisfy? Okay, so let's go back to this one here. So this was our previous version without the omega. This one was our previous version. But this doesn't work anymore, right? Because we're not running the program, we're not type checking it like this, we're not running it like this. So how do we fix that? You have a thought?
It seems that whenever we have our environments, we only need to agree with the variables that E uses. So can we do something like, if gamma is a context for E that proves that E is of type A and uses variables omega, or context omega, and eta is now an environment for omega rather than gamma? Does that work?
Okay, let's try that. Let's see, where do I put this? Maybe I'll put it here. Okay, so we want gamma E colon A slash omega, right? Because I'm going to be typing judgment. You still want eta to match.
Omega.
You want it to match only omega, okay? And then, so if this and this, then
The same statement with eta. So eta turnstile E reduces to V.
eta turnstile E evaluates to V. And, okay. And V colon A, which I want to de-emphasize for the moment. But this is no longer our dynamics judgment, because that was our old dynamics judgment. Okay. So how do we fix that? Well, actually, this is not a wrong statement. It's just we'll have trouble proving it with respect to this dynamics because the rules are different than these rules. So how can we change it? Yeah?
Do you have two etas and one being output, and the first one matches gamma and the second one matches omega?
Okay. So you have an eta prime, which matches
The first one should match gamma.
gamma. Okay, so eta matches gamma. And then we use that eta to match gamma. We get a small omega out. Okay, now what's the small omega?
I meant actually eta prime.
Okay, so the small omega, what does it have to satisfy? Matches omega. That makes sense? So somehow, because we generalize them the same way, okay, we can now relate them in the same way. And we also know something about the relation between the two, namely that the omega should be a sub-environment of eta, right? Because the things that were actually used from eta are the ones that end up in omega, but they agree otherwise. Okay? Okay, so then you can prove that theorem now with this kind of dynamics. Okay. Okay. So how do we know that at the end there is no garbage? What would that actually mean here? Yeah?
guess that for every top level computation, eta equals omega.
Yeah, so if you have a top level computation, then you should have something like, we start with eta, evaluate E to some value V, then the out should be exactly eta. What that means is that everything was actually used, right? So can we prove that? Do you have an idea? Yeah, we do some inductional proofs. So we could also say here, omega, we can prove that you have omega and you evaluate E with result V, then you get back omega if this is precise. Okay, so yeah, so we can prove that for this new dynamics, and we can show that basically when you evaluate E, everything here will be used because everything ends up being over there. Okay, so this is a really a nice way. So it gives us two things actually. First of all, it gives us a way to do type checking, okay, using rules of this nature. And it gives us a way to show that there will really be no garbage because every variable in the initial environment will have been read here. Of course, inductively, it's not going to be true everywhere because of, you know, because you take the same property into both places, but ultimately, it's going to be the case. Okay. Let's see. there anything else I want to say about this? Is there any, you guys feel like you could write down the rules for evaluation from the starting point? Yeah?
So in this, on this statement, the V and the W, are they sort of existentially quantified? The input, gamma, and theta.
Yeah, that's a very good point. So yeah, we don't actually know that this will evaluate to some V because that would prove termination for everything, which we don't necessarily have. So what we probably want to say, if this holds and this holds, let's see, what do we want to quantify over here? Existence of the W. And this, so, but what do we need to know? Yeah?
Do we actually have recursion in our system at the moment? Because we don't have defined like functions, proper lambda abstractions.
Yeah.
So without recursions, everything should terminate.
Yeah, without recursion, everything should terminate, then the theorem should be true, but then we can't prove it the way we have done it by induction over the rules. Because the termination is a complex property, you need something like logical relations to prove that. So we could prove that statement, but I want to instead prove it sort of by induction over the structure of the rules, rather than trying to do some complicated logical relation argument. So can we rescue this? Yeah, back there?
Maybe for all V to which E can be evaluated.
Yeah, so for all V, what can we say? E, whenever E evaluates to V, then what do we say about the, with some omega? So if this and this and this, then the omega matches that one. Does that make sense? Yeah, so thank you for pointing that out, because the logical structure of these theorems is sometimes tricky, okay? And I was sweeping something under the rug that I shouldn't have here, okay? Now the other theorem for without recursion is still true, but this theorem is still true with recursion. I just haven't shown you the rules because I want to avoid talking about that for the moment, okay? Okay, so if we evaluate and we get a final answer, then we have used up everything. If we have recursion, we may never produce a value, but that's okay. Then we don't have to talk about the final state. We don't have to say everything has been consumed because we never actually return the value V. Okay, okay. Any more questions? Yep.
This last statement we're now taking as an assumption that E can go to V in our semantics. But I thought our semantics can get stuck if the parallel V join omega 1 and omega 2.
Yeah.
So in a sense, now the stuckness is a precondition of soundness.
Yeah. So now this is no longer type soundness in the sense of what Amal talked about, because we're not talking about computation cannot get stuck. Okay. And in fact, it's hard to prove for this kind of semantics, but I will have a different semantics in tomorrow, or maybe 2 days from now. And for that, we can actually prove that things don't get stuck. When you have a big step semantics that says E goes all the way to a final V, it's very difficult to prove for that kind of semantics that you can't get stuck, because you kind of, the individual steps are not represented here in this judgment. Yeah?
Even hard if we don't have lambda abstractions or error types?
Well, yeah, you can make all this work with lambda abstractions, okay? But it gets more complicated because the whole notion of linearity and how you run things. So what happens is that when you have lambda abstractions, you have to build closures, you have to type closures. So it's, but you can do it. It's consistent with what we've done so far. You have your doubts? We can talk about it offline. Yeah. Yeah. It's a good concern, but I wanted to put off. Yeah, you have a question?
Yeah, can you briefly explain what ADA has gamma type, the ADA colon gamma?
Okay. What this means? Okay, it means that, So ADA maps variables to values. And what it means is that when the prescription is that a variable has some type A, then the value that X is mapped to will indeed also have type A. That's what this judgment means. So when you type something in some environment, when you run the program, the environment will bind the variables in gamma to values which have the correct types. Okay, that's what it means.
Can I ask a-
Yeah?
Will you introduce the small step semantics to this language?
No, not this language.
Okay.
I'll introduce the small step semantics for the sequence calculus because it's much easier there. But that will happen not in today's lecture. Yeah.
Does the additive approach extend to top-level definitions? I'm thinking of the case where you say you define x is equal to 2, and then you don't actually use that definition until further down. It seems like if you're only tracking the variables that are used, then when you thread the context through,
Yeah.
you lose that information.
Yeah, so there's two separate questions. So the question was, what happens to top-level definitions? And a similar question is, what happens when some variables can be used multiple times and others only once? Okay. And the whole point of using the additive approach is that, in fact, it extends very easily to that case. Okay. I don't want to look too far ahead, but we're going to do that. Okay. Basically, what happens for these top-level variables, when they appear in here, when they appear in here, you can merge them. And that's legal, okay, for those variables. So either top level or when you have variables that can be used multiple times, then this merge operation allows you for them to be used here and here. Okay. Actually, we can play a small game. So I've not introduced that yet, but affine logic is a logic in which assumptions are used at most once, not exactly once, at most once. So in fact, the type system for Rust, so I've been told, is affine, not linear. Okay. Variables don't have to be used, but they can be used at most once. Okay. So if you use variables at most once, then what happens here with the merge operation? Yeah?
Just yes, are they just duplicated, but they must be duplicated beforehand in order for them to be used more than once?
Okay. So that would be a language where you can maybe duplicate but not drop. But here we can drop it but not duplicate. Okay, so it would still be undefined if a variable is in both places, because we have to use things at most once. Yeah?
It's well defined for any subset of omega 1, omega 2.
Yeah, so what happens is that at the end, when you're all done, the judgment is something like initial gamma, some expression E, as type A, and we have to use everything. Right? When we check a top-level definition, we get our initial environment, we have an expression E, and all of these things have to be used. In affine logic, this is not going to be the same gamma, but it's going to be some omega. And the condition is that, yeah, gamma is a superset of omega, omega is a subset of gamma. So we don't have to use everything in here. Okay, make sense? Okay, so this approach is very flexible. That we can talk about logic with different structural properties. Like you can duplicate some things, you can drop some things, and what changes is this operation here, okay, the merge operation. Yep.
Just an observation. It seems like the type derivation tree is isomorphic to the reduction tree. And it seems like the typing is not very interesting. What do you think?
No, that's only because we haven't looked at interesting rules. So okay, so actually I'm inviting comments on this. So the evaluation tree is sort of isomorphic to the typing derivation. Yes or no? Yeah?
Isn't there a discrepancy for matches? Because for match, we only gonna execute one branch, but in the typing, we need to type every branch.
Yeah, so then his comment would be, well, you pick out a branch, but we already typed that branch. So actually, when we run a program, it's smaller than what we started with, right? So that's one discrepancy. They're not totally isomorphic because we pick out branches. Yeah?
Even when there's only one branch, like for unit, there's a rule that they match, unit with unit to just the body of the branch.
Mm-hmm.
And that doesn't have a corresponding.
Okay. So we have to evaluate this. This would evaluate to unit. Sorry, we would evaluate this, we would evaluate to unit, and then we'd evaluate this. But that's already, the typing derivation for that is in here, right? So that doesn't introduce a discrepancy. Yeah?
I mean, for the case of values, you're actually not doing an evaluation of typing.
For the case of values,
Or for the unit value, for example.
yeah. So there is a typing rule. The evaluation rule says unit goes to unit.
Or would you actually have such a rule? Or would you
Yeah. So maybe you would have a rule that in a context eta, when we see the unit value, we evaluate that. What's the answer for that? It's a unit value. And what is the output? What have we actually looked at?
Empty?
Empty because we have not read anything, right? Make sense? Okay. Okay. I see we're going to have to write some more rules. What would be your rule for evaluating a match? E with here x, y, and then E prime. And we start with an eta. So how would that work? Evaluate E. Okay, this gives us back some omega. Okay, makes sense? Actually, sorry, it also gives us back the value, of course. And it better be a pair of values and some omega. Okay. Now what do we do next? Yeah?
and then you'll, with an environment extended, you will match to x, y.
Eta x maps to v1, y maps to v2. Evaluate E prime to some value of V prime, maybe. And what is the environment that comes out of this? Omega prime, let's say. And here we return omega prime. Something like this? Not quite right. Okay.
You have to drop stuff from omega, right?
Yeah, we have to drop stuff from omega prime because x and y, they should be used. So they should end up in omega prime, right? And we have to delete them, yeah? Yep. So here we'd return V prime and hopefully omega prime. So one way to do this is we say x gets mapped to V1 and y gets mapped to V2. And the rule only applies if these things are in the output. Then we drop them and just return omega prime. Right?
Okay, but what about the
Which top?
So on the left-hand side, there's gamma, dynamic, blah, blah, blah. And we say we use omega. No, the left one.
Here.
Without prime.
That's the omega.
Yeah, and then we
Okay.
sequentially
Yep.
evaluate the second part.
Yeah.
And in the rule for the sequential part, so on the top level, there's another eta.
Okay. So what's the output here then?
No, I'm sorry. My question is, we're using eta in both rules
Yeah.
for the top level.
Yeah.
But we already use stuff from eta.
Mm-hmm.
Shouldn't we take out the omega in the second part?
Yeah. So that would be the subtractive approach. We'll take it out.
Okay,
The additive approach is that we put the omega in both places and we introduce some additional bindings over here. But then when we come out, this will be the things used in this computation. And this omega prime will be the things used in this computation. Overall use will be the disjoint union of those two things, right? And that should match exactly the typing rule for this matching construct, okay? Okay, so hopefully we have enough rules now that we can construct all the other ones because I actually want to get a little bit further here, okay? So it's not so easy to actually prove something like, first of all, design the dynamics so that you can prove that there is no garbage at the end. And it also turns out, I haven't thought about this before, but I think it's true. If everything is purely linear, then not much is happening in the computation, okay? Because you cannot replicate anything, right? Something interesting still happens because in the match expression, you will pick out part of some branches, so you're narrowing it down, okay? You're typing, not knowing exactly which branch will be taken. When you run it, you will take some branches. But we already know that if you have top-level definitions, especially if they're recursive, all of that changes. So another way to think about this is that a purely linear type system, unless you have some way to reuse definitions, okay, doesn't let you write many interesting pieces of code, almost none. But we have top-level definitions. And they can, so you yourself, we have written reverse and append and some interesting functions, like duplicating things. But these all require like some top-level definition. If we didn't have those, then we couldn't write very much code here. Okay. So this was a good observation. But I'm going towards a system where you have both linear and nonlinear things. So you can write your ordinary functional programs that we're used to also and just say, well, this part is linear, this part is not linear. So we don't want to really lose anything when we go to this language, but I think we want to study it by itself because studying the whole language is very complicated. Okay. So now I wanted to do something else. Yep. Okay, so we have defined something like, the question is, what is a top-level definition? X colon nat, Y colon nat, plus of X, Y equals, and then some definition for it, okay? So what's actually happening here is, okay, I'll come to it before the end of the lecture, but it turns out that these top-level definitions also have something relevant to tell us in terms of the logical interpretation of everything. And so hopefully I can remember to tell you at the end of the lecture what that is. So these don't come from, these are not arbitrary. These actually have logical meaning, and that will actually be important to our program, okay? But what I wanted to do now is, I've been talking about the logical meaning, but I have not really told you much about the logic itself, okay? So the way I want to tell you about the logic is I want to take these rules, okay? And I want to forget about the programs for the moment and just see what these rules do sort of on the types themselves, okay? So let's start with the middle here, okay? So the rule in the middle would say, I'm going to delete this because this bottom board is very hard to write on. Okay. Okay, so we have delta gamma turnstile A cross B if delta turnstile A and gamma turnstile B. Okay, and what's the next rule over there? It says delta gamma proves C if delta proves A cross B and gamma with A and B proves C. The rule at the top says that if I have A, I can conclude A if I remove all the stuff about variables and proofs. Okay. So what we have here actually is our rules that describe some logical reasoning where this is a form of conjunction. To prove A cross B, you have to prove A and you have to prove B. If you can somehow prove A cross B, that gives you license to assume A and B while you're proving C. Does it make sense? Okay, let's do plus as well. So I'm going to do the binary version of plus. Okay, so in gamma A plus B, if gamma A, and in gamma A plus B, and gamma we can prove B. Okay, so that's like a sum with two elements. So we have two rules for it because the K could be either in left or it could be in right. And then if I have delta and gamma, then in delta I can prove A plus B. And then I have, because this is a plus, this is like the sum over there with two labels in left and in right. So if I erase all this, I have to be able to prove that. And the second one is, and then over here, I get a proof of C. Okay. I think except for the one, everything is here now. Okay. So what is this plus here? Well, it's a disjunction, right? To prove A or B, you have to prove A. To prove A or B, you have to prove B. If I can prove A or B, then by cases, in order to prove C, I can either prove C from assumption A, and I also have to show that under assumption B, I can prove it because I don't know which case I'm in. Okay. So this is proof by cases. This is showing one of the cases is true. This is proving a conjunction. This is using a conjunction. And this just uses the hypothesis. Yeah?
So what in this case are delta and gamma? Are they the proofs themselves?
No, they're just delta gamma are just either no assumption or an assumption of a proposition. So they're your hypotheses that you have in your proof. So what an ordinary logic, what this judgment would say, so this judgment would say, from the assumptions gamma, I can prove A. Okay. This system, by the way, is called natural deduction. I'm just going to prove it ND. Okay. But there's a twist here, which is a twist in ordinary natural deduction, which goes back to 1935. Okay. You don't have this restriction that every assumption has to be used exactly once. But in this system, every assumption has to be used exactly once, which corresponds to the fact over there that every variable has to be used exactly once. Okay. So for example, because it's a disjoint union, some assumptions have to go here and some assumptions have to go here. I have to split my context. I can't share between these two. Similarly here, I have to split, then I assume A and B while trying to prove C, and so on, right? So because every assumption is used exactly once, okay, this is actually called linear logic. And notation is different from what I've shown you, okay? So the notation, fortunately, is this. And for the plus, we also have to just add a circle, okay? And so this form of conjunction is just cross, or tensor, as it's sometimes called, and this is just plus, okay? Because it's linear logic, but it still is logic. This is a form of disjunction, and this is a form of conjunction, okay? And the one is a form of unit. So let me not actually have to write that down, okay? So traditionally, this logic was presented first, and then people derived from that linear type system in this style, okay? But I wanted to get programming and linear programming in first, so I showed you the type system linear typing first, and showing you that what we've been doing is linear logic all along, okay? Now, in linear logic, okay, this is a very weak logic, just like this over there without global definition is a very weak programming language, because everything has to be used exactly once, okay? So in linear logic, there is one more operator. Actually, I'm going to erase some stuff here. So on the logical side, there's an operator, of course, A. So actually, let me write down all the operators we have so far. A and B are defined as the unit, a tensor B, which is a form of conjunction, which corresponds with a cross, a plus B, which is a sum, which is a disjunction, forms with a sum, okay? So in linear logic, you have some more stuff. And the other thing you have here is, of course, A, okay? And what of course A allows you to reuse assumptions, okay? So of course A is something that lets you interpret ordinary logic back into linear logic. And the way it does that is that if you have an ordinary function, let me write it like this, A arrow B, okay? Then that ordinary function would become bang A, and then this would be a linear function, which takes an argument that you can replicate and use as often as you want, okay? So we don't have this facility yet in our logic or in our programming language, except by top-level definitions, okay? So instead of having this as a first-class operator, we say we have two forms of definitions, some that are treated linearly, and these are these ones here, and another one that we can use arbitrarily often, okay, in the sense that they have implicit this way of allowing you to do reuse. So we have top-level definition sigma, and then we have a separator, and then we have the gamma, and then E as type A. So these we can reuse, or we can drop them. We don't actually have to use them. And these are treated linearly. Okay. And in linear logic, you can do the same thing, you just wouldn't have the expression E here. Okay. Okay. So the other thing you have in linear logic is you have some operators at this level. Okay. Namely, you have a form of implication. And you have another form of conjunction, okay? And these two forms also have counterparts in the programming language, okay? So these, by the way, these here are called positive. And these things here are called negative. So we've already seen, or you will see in the homework if you haven't done it yet, that for the positive ones, we don't need this operator. Okay. Why is that? Because we can duplicate and drop anything that's positive. And you can write functions that will do that for you. So in principle, you wouldn't actually need that. Okay. But when you have the negatives, these things you cannot duplicate or drop. Okay, so in other words, as soon as we introduce these, it's absolutely essential to be able to have that operate at the logical level. Okay, but logically, you can prove things like 1 plus 1, okay, proves that 1 plus 1, okay, tensor 1 plus 1. The logical proof of that is probably which function? It would copy a Boolean, right? Because this is the type of Boolean, 1 plus 1. This injection on the left would be true, injection on the right would be false. And this means a pair of Booleans. Right? So one implementation of that would be something that copies Booleans. Okay? So that would be, logically, would be a proof. If we write it down as a, with an expression, it would be a program that takes a Boolean and gives you two Booleans, yeah?
Would a program that returns just false, false also be a proof?
Yeah, that would be another proof. So it doesn't have to duplicate from the type you cannot tell exactly what it does. So you could return false, false, right? And it would still have that type. Make sense? But you can't just return false without looking at it. You have to look at this thing. You have distinguished cases. In each case, you can return fair, false. Works. Okay?
Can you repeat how you prove this using the logic?
Okay, how do you prove this using the logic? Okay. So 1 plus 1 proves 1 plus 1. This is the rule of hypotheses. Now you use proof by cases. You have two cases. In the first case, you have 1. And you have to prove all of this. And in the second case, you have to prove exactly the same thing. You have to prove this twice. Right? How do you prove this? Well, the rule I haven't shown you, but there is a rule for 1 that says with no assumptions, you can prove 1. And another rule that says if I have delta and gamma, and from delta I can prove 1, then and from gamma I can prove C, then from the combination of these I can prove C. Okay? So now you have to use that here to get rid of the 1. So what you do here now is you from 1 you prove 1. And in this rule, that consumes that assumption. So now nothing is left. In the empty context, you have to prove 1 plus 1 tensor 1 plus 1. Now you have to split up your context. There isn't anything. And you have to separately prove 1 plus 1 and 1 plus 1. And now you can prove that by proving 1. And then you're done here. And now there's different proofs, which it's hard to see in this formulation, but this could be the first plus introduction rule, which uses this one here, or it could be the second one, which uses this one here. And in the logic, it doesn't matter, but in your programming language, those would be different. One would have a true here, and the other one would have a false here, depending on how you interpret 1 plus 1. Okay. So from a logical perspective, this is a stupid proof. Okay. But computationally, these things are meaningful. Right? So when you work in constructive logics, it's not just the fact that you can prove something, but exactly how you prove is really important. Okay? Because the proof corresponds to a program, and the program really matters. So like the type for and or in your homework, they're the same type. Takes a Boolean, and a Boolean gives you a Boolean. But of course, they're different functions. And so they correspond to different proofs. It's very hard to see if you just look at the proof. So instead, you write the program. And then there is a mechanical procedure where you can take the program And you can extract the proof from it if you want to see what it is. Okay, because when you have a typing derivation for a program, the way you get the proof is you erase all the stuff that has to do with the program, all the variable names and all the expressions, and you get a proof over there. Okay, and this is a remarkably robust phenomenon that works for many different logics. As long as you make sure that the logic is constructive, then you can relate the constructive logic to the programs in some kind of programming language. Okay, and this is a particularly simple instance. So I'm almost out of time. So I wanted to show you the rules for these two things, and then I'll finish. Okay. So actually, let me show you the logical rules. I didn't actually use this part here. So these rules will look different from the rules we have seen so far. And there's a good reason for that. Okay. So if you have a context gamma, and we want to prove A implies B, okay. How do we do that? Well, we assume A, and we have to prove B. Because the logic is linear, it means that this assumption A actually has to be used in the proof of B. So for example, if I try to prove that A implies that B implies A, I will not be able to prove that for arbitrary A and B, right? Because I assume A, and I assume B, and then I try to prove A, but the assumption B will never be used, so that will fail. Okay, and then the other rule is kind of strange. So it says something like, if I have proof of A implies B, and I have a proof of A, then if I put the resources together, gamma and delta, my hypotheses together, I get a proof of B. So what's strange about this is that unlike the other rules we've had that eliminate something, okay, it's not really like a match-like thing, okay? You don't actually create a fresh assumption over here. You just combine these two things, get the proof of B, okay? Okay, one more thing. Actually, let me do the proof toward expressions for these. This, as the notation already suggests, is a function that takes an argument of type A and gets a result of type B. Okay. So with expressions, it's going to be lambda x dot E has type A arrow B in a context gamma if the context gamma with x colon A, E has type B. So the way that it's the reason it's a function, we'll just use notation from functional computation from the lambda calculus to denote this function. Okay. Yeah.
Is this a linear arrow or a regular arrow?
Yeah. So in this programming language, I'm not distinguishing between those, but because everything is linear, it's an ordinary arrow, but it is treated linearly. Okay. The reason I don't distinguish because later on we also have functions that can use their arguments multiple times, or functions that can drop their arguments. If you distinguish all of them with notation, you get like this whole huge zoo of different arrows. Okay, so I'll just have one arrow, and we distinguish them based on what the variables essentially are. Okay, and then what is this one here? Well, in delta, I have some expression E1, which is A arrow B. And in gamma, I have some expression E2 of type A. Then in delta, together with gamma, I have E1 applied to E2 as type B. So using a function is just function application. Okay. So an interesting thing about this is that with these constructs that we have here, okay, we are actually observing the structure of our expression. The way we observe the structure of our expression matching against it. So this will be one of these k's, and we're observing which case it is by picking out the right branch. So we're looking at the value, and we're observing what the value is, and we're distinguishing based on what it is and continue to compute. Now functions are different. Inside the language, you have no way to observe the structure of a lambda. All you can do is you can apply to an argument and see what happens. We can't pattern match against the lambda expression. Okay? So we can pattern match against things like these pairs. We can match against injections. We can pattern match against a unit element. But we cannot pattern match against a lambda expression. Instead, we can apply it. Okay? So this is a fundamental distinction in programming languages between the positive and the negative types. So these types here, up in the first line, these are positive, which means you can directly observe their structure. And these are negative, which means you cannot observe their structure directly, but you can interact with them. Like you can take a function, you can apply it and see what happens. Okay. So based on that discussion, what do you think the elements of this type A with B should be? This is by, yeah, it is pronounced A with B, but it's also a form of pair. What should be the elements of that type? Yeah?
Is it a call stack?
No. But that was a good guess, actually. So let's look at the logical rule, okay? So the logical rule is, okay, in context gamma, A with B is true. If in context gamma A is true, context gamma B is true. You object. This is not linear. We're duplicating gamma, right? But we already had a case like that where we're duplicating gamma, which wasn't the case expression here. In the magic expression, we duplicated gamma into each branch. It was okay because at runtime, only one of the branches was taken. Yes? We have to achieve the same to make this sound. We want only one of the branches to be taken. How do we do that? Well, if in gamma we get A with B, we can extract an A. Or in gamma we have A with B. We can extract B. But because things are linear, we can only like extract either the A or the B. We can extract only one of them, but not the other. And therefore, just like for the case construct, it's going to be sound. And in fact, we have to duplicate the gamma here because we will extract only one over here. Now, what is the expression assignment for that? Okay, so this would be, I'm going to write it like this, E1, comma E2. If in gamma E1 colon A, and in gamma E2 colon B, and then what's the assignment here? Gamma E colon A with B. What would be a natural way to write this thing of type A? E dot pi 1. So we take the first projection, okay, of the pair. You get something of type A. And here, in gamma, we take the second projection to get something of type B. Okay. What that means then is that this thing here is a lazy pair. We don't evaluate these expressions underneath. They're arbitrary expressions. Okay. We cannot match against their structure because it's lazy. But we can extract the first component, or we can extract the second component, but we can't extract both of them at the same time. Okay. And that preserves linearity overall. Okay. So when you actually see this, I wrote this right below the plus, because you can generalize this to a lazy record. And what would that look like? it would be this L colon A sub L for some finite index set L, okay? And then the introduction rule would say in gamma, if you have a record L equals E sub L over some index set, that would have type of this lazy record. For this to be the case, in the same context gamma, each expression has to have type A sub L. This would be for all L in the index set. And then the rule to eliminate that would be if I have an expression which has this type, L colon A sub L, L in L, then in gamma, okay, E dot the label L, actually I should underline these because they're from, they're labels just like for the sum. So if I project out the nth element, then get what, actually let me write K here. What is the type of that? A sub K. And for that to be the case, I need to be K, be in the label set. Okay. So that means that a counterpart to the sum is this operator A with B, sometimes called as external choice, okay? Or you can think of it as a lazy record. It's a record of a bunch of branches. And you can, in the linear case, you can project out exactly one of these branches. Just like from the sum, you can take exactly one of the cases by taking out one of the branches. Okay. So the thing I want you to take away here is that in linear logic, we have positive and negative types. The positive types are things we can directly observe the structure of. Because we can do that by pattern matching, we can actually drop or duplicate them because we can look at their structure and then, you know, recurse all the way down, get rid of it. So because we can observe them directly, we can actually duplicate them. These are negative. We can't observe them directly. We can't see the structure of a function. We can't see the structure of a lazy record. All we can do is we can project out a component or apply a function, okay, and see what happens. Because that's the only thing we can do. We cannot actually drop or duplicate functions. Okay. Yeah, and these are the typing rules here for these new constructs. Okay, this is for the labeled external choice of lazy records, and for functions, they're the ones over here. Okay, so I can't do that today, but in the language level 1, which I just introduced, okay, you will have ways to express, use negative types. Okay, and so at the beginning of the next lecture, I will do some live coding now, actually being able to use these first-class functions, okay, and also using these lazy records. And what you use the lazy records for when they're recursive is object-oriented programming, okay? Because an object is kind of a lazy record, and applying methods will pick out some parts of that, pick out a method. And of course, this is the function used well for functional programming, right? So now it really is functional programming because we have functions now, okay? Before it was functional programming without functions. It's a little bit limiting, okay? But we will see it's actually hard. So for example, the map function, right? You map a function over a list, it's not linear. Because the function f, how often is it applied? N times for a list of length n, right? It's applied to every single element. So a map is not linear in the function. So map is not linear, so that's a problem. So we have to deal with that, right? So functional programming with the constraint of linearity is actually pretty interesting. There's some new challenges. So we can write something that's like a map, okay? We'll see how that works. So we'll now do some interesting functional programming type things at the beginning of the next lecture. Okay, now we have our language complete. The only thing that we don't have yet from linear logic is the of course A. So we have a pale image of that by top-level definitions. Anything at the top level, implicitly, you can use as often as you want. You can make a top-level definition, not use it. Or you can make a top-level definition, use it as often as you want. That's OK. So we have a weak version of that. OK. And eventually, lecture 4 maybe, we'll have the proper version of that as well. So we can model all of these things. At the moment, we can model these things and some kind of restricted version of that. Yeah, so like I said, I encourage you to do the linear programming. Even without functions, it's still interesting. Okay. And I know that some of you already handed in stuff, and it works. Okay. So that's good. Some of you have handed in that doesn't work. That's also good. It means my work was not entirely in vain. Okay. All right. So I'll see you guys tomorrow.